Let's first take a look at the dimension reduction. So it is a slide, okay? So please download the slide PCA and LDA. Okay. It is an old slide, but all the necessary materials that I would like to share with you, which is Principal Components Analysis, PCA, okay, in short. And what is PCA? When we analyze our data, okay, it looks like a table, right? We draw it a lot of times. We have several samples. For example, we have n samples. Okay, we have a lot of features. Okay. For example, if we have n features, okay, and usually we have a target y, which could be category data or numeric data, so that we can do classification or regression problem. Okay, usually, okay, when we analyze the data, the size of n, okay, it should be hundreds of data points or thousands of data points and even more. It depends on what kind of data you have and how did you collect your data, right? Hundreds of data, thousands of data, even millions of data. Okay, and what about these features? Okay, how many features we should have if we like to analyze, for example, human being. For example, you like to describe a human being. In what kind of feature you like to use? For example, height, weight, male, female. There are a lot of features to help you to describe different people, right? And if we like to distinguish different data points, which means we like to distinguish different people, okay, we should have enough features to separate different data points in the n-dimension space. 好，中文再讲一遍啊。如果你想要有足够多的 features 来描述一个人的时候，你以人为例子。那身高、体重啊，什么男生女生啊，他是不是学生啊？那我们在 M space 这个空间里面，你应该起码要让每一个资料点要能够被分开嘛，对不对？你才能够去分辨两不同的人。所以其实如果你的群体很大，比如说你有台湾好有2300万个人，你想要让2300万人在这 M 的 feature 里面都看起来有不同的值的话，那你 M 一定要够大嘛。要不然你很容易找到一个人，身高一样，体重一样，性别一样，念的学校从小到大念的学校一样，然后薪水也一样，然后工作也一样，那你就没有办法区别那两个人，没有办法区别 data point 里面两个人是一件很危险的事情，好吗？因为他们的 Y 可能不一样，可能一个，比方说有结婚，一个没结婚，但是他其他全部 X 都长一模一样，这样对资料来说是比较危险。我以后再讲一遍好了。For example, if you have, for example, Taiwan has 23 million people, okay, in Taiwan. So if you want to describe all the 23 million people by using this table, okay, at least you have to differentiate all those people by using these n features. It is possible you can find two persons, okay? They have all the same features, but they have different y target. So this is very dangerous if you have such kind of data. If you want to differentiate these two people, the best way you can do is to add additional features to differentiate these two persons. But however, most of the time we create too many features in this table. For example, if we have thousands or even 10,000 of features to describe your subject, 我们有甚至可能用到10万或是上万的 features 去 describe 你这个subject， 就是你的目标，你的目标，这个也太多了哈。So that this table will be very, very big, and from the computing aspect, it is very difficult, and it takes a long time to train your model to test your data. So what we can do? We can do dimension reduction. I have n dimension data, but some of the data columns, which I mean columns, maybe they are useless. So I don't want to use useless features to describe my data. Okay, and I'd like to remove them from the data set so that I could have few features, so that when you make your model, it would be more easier to do so. Okay, we have an assumption. Okay, PCA is concerned with explaining the variance covariance structure of a set of variables. What does that mean? For example, if this is height, okay, and that x2 is weight. Usually we believe, okay, that is our observation. We believe your height and your width should have some relationship. For example, linear relationship or something like that. So the covariance between features, which is x1, x2, will be very, very, very high. 我们一般认为，比如说你的身高跟体重应该有极高的 covariance 就是相关性，极高的相关性。所以有的时候你只需要用一个 feature 来描述你的 height， 你可以用数学算式去导出你的 weight。比如说我们随便做一个线性的那个 regression， 好吗？所以就变成说，在所有的 features 里面，说不定有一些 feature 跟另外一些 feature 它们高度相关，它们几乎可以用线性或是一些其他的方式来阐述两个 feature 之间的关系。所以你只要保留其中一个 feature 就好，因为另外一个 feature 可以用导的，好吗？所以我们就借这个应该说这个 concept 吧，好，我们想办法把这个 m dimension 尽量往下降低一点，少一点，来分析比较方便，好吗？好 ，so maybe there is a linear combination of those features, so that I can represent the original x2, for example, your weight, by using x1, which is your height. So that I don't have to keep all the features, so I can remove some of them. How do we know which dimension, original features, okay, original feature, original dimension, can be removed from the data set? 好，所以我们现在决定就是说，到底哪一些 features 是可以被 remove 掉的 ？Okay, here are some steps. First, okay, you have your original data, which is this table, right? X1 to xm, and we have n data points. Okay. The second step, standardize the data. Okay, which means your average should be 0, and your standard deviation should be 1. Okay, so you have your weights, you have your heights, and you do standardization. Still have n data point, right? But you have x1 prime, okay, x2 prime, okay, and original data, for example, the average maybe it is 170 centimeters, and your standard deviation is, for example, 13, okay, and your weight maybe that is 60 kilogram, okay, and your standard deviation is 8. To make it standardized, so that your average standard deviation should be all zeros, and your that should be 1. How did you do that? So 180 minus 170 divided by that is the z-score, right? Usually we don't do it by ourselves, so you can just ask your tools, for example, Orange or your Python package, to do the standardization. You just second step, calculate the covariance matrix. So we'd like to evaluate the relationship between features. It is a matrix. Variance between x1 and x2, x1 and x3, x1 and x4, and so on and so forth. Calculate the eigenvectors and eigenvalues of the covariance matrix. Okay, I believe you have learned eigenvalue and eigenvector when you in something like operation research or operation management class or business mathematics， 就是商业数学啊，或是线性代数，或者是 OR 跟 ON 里面应该都有教，怎么求 eigenvalue 跟 eigenvector。Okay, but it is very difficult to imagine what kind of calculation would you like to do right here. So let's take a look at an example, which is actualized figures. Okay. First, we have a table, right here. This is the original table. We have 4 features, W, X, Y, and Z. Okay, and we have a lot of data points, n data points. Okay, and for each column, we have their average and their variance. Okay, variance 跟 standard deviation 没有差嘛，好，猜得更好。What Pca does to this table? Pca redistributes features variance. Okay, it's very difficult to imagine. Pca 这个动作是做什么？我们有左边的这个表嘛，对不对？然后我们刚刚说过，左边的这个表基本上我们已经重新整理过了，就是它的平均值跟它的标准差已经整理过了。这个不过整理平均值跟标准差不是什么太大的事情，就是资料 资料会被压缩在一个比较小的范围里面啊。不过压缩并没有改变资料点之间的相对关系啊，这个是原本的图哈。好，那 Pca 要做的事情是呢，它会重新的分配哈，就中文就是重新的分配什么呢？那些 feature 的 variance， 就是那些 feature 的变异数。所以它每一个 column 会有一个 feature 的 variance 嘛，对不对？V W V X V Y V Z， 你有4个 variance。A variance 它的意思指的是资料的分散性嘛，对不对？好，大家统计应该都还知道嘛。好，你的 variance 越大，你那个 column 的那些值就离你的平均值越，不能说越远啦，应该说越散啊。有些值会落在平均值附近，有些值会落在离平均值很远的地方。然后你的那种离散的程度越大，你的 variance 就越大，对。所以如果你有个 column 它的 variance 很小，非常非常小，表示大部分的值都集中在平均值附近嘛。好，你看这个概念没问题吗？好，因为我再讲一遍哈。If you have a column, if you have a feature which is W, for example, and its variance is very, very large, which means most of the data point from 1 to n, they are far away, most of them, far away from their average. Okay, something like that. For example, if I have a W like this, and if I have, here is the average. Okay, if you have a very large variance, your data, okay, might be a lot of data is far away from your average. Of course, there are some data still near the average, but on the average, your data is far away from your average. For example, if you have another data point and you have a very, very small variance, which means most of the data are around your average, okay, not far away from your average, okay, that is the basic things, okay. And most of the time, when we talk about variance, if you have a data column, okay, you have a feature, okay, which has a very, very small variance, which means this column cannot, okay, beware of my words, cannot differentiate those data points because they have smaller variance. Most of the data points are very crowded around the average, right? If you have a data column, okay, you have a feature which has a very large variance, which means all the data points are far away from your average. So in this data column, you can differentiate those data points. 好，中文就是说，如果你有一个比较大的 variance 的资料的 column 来说的话，因为 variance 比较大嘛，所以资料全部散开嘛，资料比较散开的话，你就比较能够区分每个不同的点。比如说，全台湾的总资产好了，你会发现很有钱的很有钱嘛，就散得很开嘛，啊，不有钱的就不有钱嘛，然后中间很多嘛。那比较集中的像什么？比如说像体重好了，体重这种东西啊，就40到80-90之间。所以你发现点那个全台湾2300万人的体重全部点在数线上，它会非常的拥挤，它会非常的拥挤，所以你就比较不能够分辨那些点。那一般来说，我们会认为，如果你有个 column， 好，有个 feature， 它能够把大家都散得很开的话，表示这个 column 对大家的分辨能力比较好，因为大家都散得开的嘛。好，比如说一个班上如果有一个 column， 好，就是我们讲全部都黑头发。那这个所有人都点在黑头发那个点啊，没有人在那个点之外，那黑头发这个 feature 实际上就没有办法分辨大家，没有办法分辨大家，别人的超小就没有用，因为我们说嘛，我们资料分析的目的就是把大家都好好的描述很好，然后分开。可是如果大家都集中在某个点上 ，variance 都很小，你就没有办法把大家分开。好，这是概念上的意思啊。So that if you have a column which has a very small variance, for example, your hair color. All of the students in this classroom, they have black hair. So all the data points are plotted in the same place from the perspective of this dimension. So that we cannot distinguish students in this class because all they are in black. We generally believe that if there is a data column that has a very large variance, so that we can distinguish different data points. So that column is more valuable than the other columns. We have 4 different features right here. Right, we have their variances right here. So basically, the feature who has larger variance, which is more valuable when we do analysis. What Pca does is that we can do space transformation， 中文称之为空间转换。Okay, space transformation. We create 4 features, which is called PC1, PC2, PC3, and PC4, 4 dimension, right? And still, we have n data points right here. And we do linear combination, which is right here. So PC1 equals to a certain linear combination of the original Wx, y, z. Okay, and so on and so forth. We have 4 formulae right here. Okay, what does that mean? When we do linear combination in space, it means rotation. 我们创造4个不同的 features， 叫 PC1 到 PC4。好，那它们的组成呢？你前面公式这边有写嘛？它就是一个原本的那个空间 wx、y、z 的线性组合。好，赶快回想一下你们以前学三角函数的时候啊，你记得吗？如果我们要在三角函数里面让那个坐标轴，比如说向左边转一个西塔角度的时候，刚刚老师已经有教你，那个坐标轴的转换就是x乘以 cosine 西塔，然后再乘一个 sin 西塔的值，你就可以把那个东西旋转一个左转逆时针一个西塔的角度。所以实际上旋转这件事情，只是靠简单的三角函数的公式里面就可以知道它是原本的 x 跟 y， 然后乘上一个系数，那个系数是 cosine 西塔跟 sin 西塔的值，它就可以旋转所以呢，你注意看到，我们现在原本有个空间，对不对？是4维的空间 wx、y、z， 然后你就赶快想象上面有很多点，对不对？然后我们刚刚不是说我们第一步跟第二步要做什么？要做平均变成0嘛，对不对？平均变成0就是好，现在想有一个4维空间中间有一团云云里面有很多点，云是不是有个中心点，对不对？你把那个中心点移到原点身上，可以吗？做个平移。平移的意思其实就是把平均变成0的意思。然后你那个云可以做收缩，如果云原本长长的，现在你把它收缩成一个圆圆，好，然后我们要做什么呢？我们现在要做资料的旋转，因为这是一个4维空间嘛，比较难想象，所以就开始旋转的资料。旋转资料比较不好想，你现在就想，你现在眼睛不是看着那朵云嘛，然后你不是可以穿过圆心嘛，对不对？你现在开始改变你的视角，比如说你可以从 x 轴往云那边看，你可以从 y 轴往云那边看，可以斜斜的看，可以从后面看，这个所谓的改变视角。就是我们人换了视角，资料没有动嘛，那么人不是换了视角。那实际上你也可以把它想象成你人在正前方没有动，往圆心那边看过去，可是你把那个云做任意的旋转。所以我们刚刚做了平移缩放现在还做了旋转。所以资料就从原本的一个形态换到了圆心上，变得比较圆，然后你还可以对那个圆做个旋转。那你因为人很妙人的视角就那个角度往下穿过去看嘛所以你就会看到那个资料，那个云那个云的资料在那边被你旋转，所以你可以从任意的角度看那些资料，好吗？这个是所谓的旋转意识。旋转超简单，就只是靠那个线性组合的公式的改变。那至于说你在每个轴wx、y、z 的轴，你要旋转多久多少角度呢？那就看前面那个系数 a1、a2、a3、a4、b1、b2、b3、b4、c1、c2，那就叫 b1、b3、b4。所以实际上呢，这个 A、B、C、D 它是一个矩阵嘛，对不对？然后有四个维度嘛它实际上就是代表着旋转的角度的意思，好吗？所以你的资料呢，就从原本的 wx、y、z 现在变到 PC1、2、3、4，因为你旋转过之后，你的那个轴嘛 wx、y 的轴全部都被你旋转过了所以你的资料会画在新轴上，所以新轴会对这个资料会有描述点，那外面右边就变成这个样子。所以中间就只是旋转而已。那那些 A、B、C、D 要怎么旋转？那等一下会讲，好吗 ？So let's explain it again. Okay, we talk about Pca Redistribution. Okay, basically wx,y,z is a 4 dimension, right? There are a lot of data points in that dimension. So you can imagine that you have a lot of data points, okay, in the 4 dimension space. First things, okay, you have to do, as we mentioned before, you can move your entire data point. Okay, maybe we use the word cloud. Okay, maybe a lot of data point in the cloud. Okay, you imagine there is a cloud in 4 dimensional space. You move this cloud to the original point. Original point 就原点to the original point. Okay, so you move the data from somewhere to the original point. Okay, which is exactly what we do in step number 2, standardize the data. So the average will be 0 because you remove your data to the origin point. So that's the first thing you have to do. And then when you do this Pca redistribution, that means you move your point of view, 就是你的视角 around this cloud, so that you can observe your data from or any angles to observe your data. The data you remove from somewhere to origin point, and you move your point of view around this cloud to observe the data. For different angles, how did you describe such kind of angle? You use the A1, A2, A3, B1, B2, B3, and so on so to D1, D2, D3, D4 to describe how do you move your point of view. Maybe you have learned that before. In a 2D surface, if you want to rotate your axis, 就是你想转换你的轴 and you can use a very simple function, x cosine theta plus y sine theta to move, to rotate your original data point to a new axis. So it's the same. We only need some parameters. For example, here is A1 to D4, so that we can rotate our point of view to observe the original data, which was described by Wx and Yz. However, now we have new axis, 就是我们有新的轴, and we name those axes as PC1, PC2, PC3, and PC4, which is principal component 1, principal component 2 to principal component 4. So that principal means new axis. 有新的轴啊，好吗？好，所以我们有一个转换视角的功能，对不对 ？Okay, and you have to know that even if we rotate our point of view, the relationship between those original data points is still the same. 好，中文再讲一次哦。即使我们转换视角在观察这个资料，但是那些资料点只是被旋转而已啊，它们彼此之间的关系，所谓的关系就是远近的距离，实际上是没有变的，对不对？你想嘛，随便在平面上随便点两个点，然后你把它向左转18度，那两个点的距离有变吗？没有变啊。你不管怎么旋转啊，它们距离是不会变，因为它们是绕着圆心旋转，好，这点很重要。For example, if you have a 2D surface and you have 2 data points, okay, around the original data point, okay, if you rotate the axis or you rotate the data, the relationship between these 2 data points, which is the distance between these 2 data points, is still the same because they rotate around the original points. Okay, so the relationship between those data points is still the same, no matter how we rotate this cloud, okay, or how we rotate point of view, 可以吗？啊，不论你怎么旋转，它们资料原始的关系是不会变的。Okay, since the relationship between these data points is still the same, we have a very magic thing right here. That is very, very important. The variance of the data point in the original space, which is V, W, V, X, V, Y, and VZ. Okay, that is the summation of the variance of this n data point represented by original axis, which is W, X, Y, and Z, is still the same as, at the right hand side, all those n data points in the new space, which is described by PC1, PC2, and PC3, and PC4. Since we just do the rotation, right? So the variance, which means the relationship between those data points, is still the same. So the sum of the variance in the new space, which is VPC1, VPC2, VP3, and VP4, the summation of these variances are still the same, which is right here. 好，中文再讲一遍哈。既然我们只有在原本的空间里面做了一个旋转，好，我们做了一个旋转，它就变成新空间了。好，因为我们会有新的 x 轴、y 轴、z 轴，现在就是 PC 1、2、3、4。好， 既然旋转不会改变点之间，要记得旋转指的是绕着原点旋转啊。既然绕着原点旋转不会改变彼此点跟点之间的距离关系的话，那也就是表示我们讲关系嘛。原本在 w_x_y_z 啊，你就会原本有4个 variance v w_x_y_z 啊，这4个值的和啊，那也就是说原本资料点的变异数的和，就会跟你的新的资料点你的资料点就是1到 n 嘛，在新的维度啊，就是 PC1234，它的 variance 就是 VPC1234的和要一模一样。你不会因为你旋转了点而增加了新的 information， 所以新的 information 是因为彼此之间的距离根本就没有变，对，彼此之间的距离根本就没有变，所以关系就没有变，关系没有变 ，variance 就不会变。所以就你在原点做旋转的话 ，variance 的总和啊，在原本的4个轴，跟在新的4个轴会是一模一样，这是数学可以证明的哈，但是我们就不证明了哈，因为这个比较麻烦。OK，so the sum of the variance in the original space, which is wxyz, is the same as those data point in the new space, which is PC 1, 2, 3, 4, is the same because the relationship between these data points does not change. So variance does not change. So the sum is the same. The sum of the variance is the same. Okay, but how do we do this kind of rotation? How do we define A1, A2 to the D3, D4? Okay, there's a very important things of Pca, which means when we do the rotation, the data rotation, okay, the space rotation, okay, we request. So make sure you understand that. That is our request. That means could we find an algorithm to help us to find such kind of rotation, such kind of new axis, so that, okay, see that the variance of the first new axis, which is PC1, VPC1, is larger than the second axis and third and fourth. 所以中文的意思是说，我们现在在做一个数学运算嘛，我们可以找一个演算法。当我们在做空间转换的时候，我们可不可以找到一个新的轴 PC1234，使至于我们新转出来的那个视角嘛，新转出来那个视角，在第一个轴上，就是 PC1 那个轴上，它拥有最大的 variance， 然后我们去决定第2个旋转的轴PC2， 那它会有第2大的 variance， 然后第3、第4。然后一直往后，那看你，因为我们没有做空间的变换，所以四个维度你转出来一样还是4个维度，所以就会有4个轴，4个新的那个轴，4个新的轴。那我们是要求演算法告诉我们说，算出来的那个轴第一个 variance 最大，第2个，然后次之，然后再一直往后，这是中文的解释。OK，so let's take a look at an example. Okay, right, the next one. So, for example, okay, the figure at the left top side, 就是左上角这个图呢 is the 3-dimension space, right? And there are several data points right here. Is a red data points right here. Okay, so that I can rotate those data. Okay, at the right hand side, the top figure. Okay, it is one of the way to rotate the data. Okay. For example, that is figure A, that is B and C. Okay. For figure B, okay, you can rotate your data point, your point of view, or you can rotate your data so that on one of the axes, which is this time black one, that's Y, X, Z, right? So that is, for example, W. If you rotate your data and you find a new axis, okay, so that you can measure how wide, okay, the data point on this axis. 中文是说你可以旋转资料嘛，你 always 可以找到一个轴嘛，对不对？然后我们讲这个轴现在叫 W， 那这个轴的 W 呢，你就可以看嘛，原始的资料点你一定可以project， 就是直接投影在这个轴上。那投影在这个轴上之后呢，你就会在这个轴上得到，比如说最小值是多少啊，最大值是多少啊，然后这个宽度是多少，你可以 evaluate 它投影在这个轴 W 轴上的时候，它的平均值还有标准差跟变数是多少，这个都可以算出来的，对不对？因为就做投影就好了。 好 so that is one of the example which is W. And of course you can find another axis, for example, V. Of course you can find another axis which is V. OK? 那你可以继续旋转你的视角，你 always 可以找到另外一个视角，然后另外一个轴，然后你把原本资料点就投影在那个轴上。好 ，and you can always find another axis. Okay, and you can project your original data point, which is the red one, to this axis, 就是 do projection. Minimum value on this axis, the maximum value, the average value, the standard deviation, and variance, so on and so forth. Okay. From our opinion, okay, as I mentioned before, if I have a data column, if I have a feature that can separate data points, which has a very large variance, that means this column will be very, very useful to distinguish the data point. So that PCA is trying to find how can we rotate the original data point so that I can find a axis, which is like the graph C. Okay, so we would like to find the widest distribution on axis V. 好，就是我们 PCA 的目标，就是你要找到一个，就是在众多的维度里面找到一个 V， 比如说一个 V 的维度，它会有最宽的资料的这个 spectrum。啊，最宽怎么形容？就是 variance 最大。那 variance 最大的话，我们前面介绍过怎么样？一个 data 一个资料，如果它 variance 最大，我们就可以区分那些原本的资料点，那它就越有用，因为我们把东西分开了，好吗？分开这件事情在这份里面是很有用的。如果东西全部都挤在一起，那个资料点就比较没有什么用。So that if we find the largest axis V, okay, it has the largest variance, and then we fix this axis, 就是我们固定这个轴 and we do rotation again and try to find this U axis. 你可以想象哈，就是说你现在有个资料一个资料的云的样子，对不对？那你就不管怎样，你赶快去转换你的视角，然后找到一个最宽最大的一个轴。好，按我们说最大的 variance 很有用，对不对？好，那就把它固定住，好，这来说是 V 嘛，就把它固定住。那因为这是个多维的空间嘛，你把这个轴固定住之后，你是会对那个轴做旋转。看啊，你有一个轴，它看起来最宽，那就把它固定住，然后它像保特瓶那样，你就旋转那个保特瓶。那你旋转之后啊，就像下面这个图这个样子，你是不是可以找到在某一个角度某一个观点？它在跟它垂直的那个轴上，你可以右转出一个最宽的，就是散的最开点。所以在这个二维平面上，那些红色点点啊，全部会散得最开。那你这样就可以找到第二个轴嘛？以这个例子来说是 U。好，那接下来你固定这个平面，那你开始旋转，好像是很难想象你的第三个轴。那一样你可以在那个四维空间里面去旋转那个二维的平面，你可以在旋转找到一个又最宽，然后又跟这两个轴是垂直的，这已经非常难想象了哈，因为我们不是生活在四维空间里面哈。你可以想象你在二维里面，你可以找到一条线，你可以旋转它嘛，然后再找到另外一个垂直的，让资料上最开。所以在四维空间里面，你应该是可以针对这个平面，然后做一个很莫名其妙，我也不知道怎么旋转，它可以在第三轴上也是垂直这两个轴，然后让资料上的最开。然后一直往下走。Okay, you can imagine that. Okay, you have data point and you fix the first axis, which has the largest variance, and you fix its axis, and you continually rotate your data point. So like you can find another axis which is orthogonal to the original. Orthogonal 就垂直的意思哈。Orthogonal to the first axis. And then, for example, this axis U, has the second largest variance. Okay, because you fix the first axis and you rotate the data along with this axis and you find the largest one. Okay, in the next dimension, U and V are orthogonal. And then so on and so forth. And you fix this surface, okay, which is described by V and U, and you do the rotation in the fourth dimension space, and you find the third axis, which has the third largest variance, and so on and so forth, By doing this, the original data point, which is the left top side. Okay, the original data point will be described by the new axis. 就是你这样子慢慢这样做之后，你找到第一个轴、第二个轴、第三个轴之后，你会发现原本的资料点，它就会比较均匀的散在第一个轴、第二个轴、第三个轴、第四轴，因为我们就是这样找到第一个轴、第二个轴、第三个轴、第四轴的嘛，对不对 ？Okay. So that let's come back to the this slide. Okay. So we have new axis, right? PC1, 2, 3, and the relationship between these data points from 1 to n is still the same. So the variance is still the same, but we request the VPC1 should be larger than 2, VPC2, VPC3, and VPC4. And sometimes in practice, how many dimensions we have? As I mentioned before, maybe hundreds of dimensions, features, maybe thousands of features or dimensions. But as I mentioned before, some of them has a very high covariance. So not all the features are useful when we analyze the data. So most of the time, for example, we have 100 features. However, as we mentioned before, the summation is the same, right? For example, if this summation is, for example, 100, for example, okay, if 100. So that, for most of the time, the first VPC1, its variance is very large. So maybe, okay, let's just say an example. Maybe it has maybe 40% of the original variance has been described by the new PC1. Okay, originally maybe that is 20, 20, 20, 20, and the rest of them are 20. So the summation of the variance in the original space is 100. For example, the sum of variance is 100. However, because we redistribute those variance by using VPC1, VPC2, so maybe VPC1 it has 40% of the original variance, and maybe VPC2 has 30%, and so on and so forth. All the other dimension, they only has 20% of the variance, of the original variance. Okay, and most of the time, okay, it's more like this. Some of them has 20% of the original variance, and the rest of them are very small, even zeros. Of course, the summation is still 100, but we redistribute all those variance to a new space, PC1 to PC100. Okay, in this case, we can do a very simple thing, which we may manually divide the data with a parameter k, which means PC1 to PCK. At this point, if the summation of the variance of PC1 to PCK is large enough, for example, 90% of the variance has been included in PC1 to PCK, and we only keep those features, which is PC1 to PCK, to do the further analysis, and we discard all the other dimensions from PCK plus 1 to the end of to PC100, for example, because these features only have maybe 5% or 10% of the variance of the original data. That is very useless when you do the data analysis. So that we do such kind of things by using PCA. 所以我再讲一遍，我们就要停了哈。我们通常的做法是这样子嘛，因为既然说我们可以把比如说原本的100维东西切成一个新的100维，然后我们把 variance 已经排好了。那 variance 排好，因为我们刚刚在转那个视角的时候都是找最大的 variance 嘛，对不对？所以非常有可能的就是说，第一维啊，就是新的第一维 PC1 的这一维，其实已经占了原本的variance 的40%了，然后 PC2 又占了30%，PC3 占20%，它其实已经占到原本100%的 variance 的总和的很大一个量了。所以在实务上我们是这样做的，我们会切一刀 K， 然后在前 K 的 dimension， 或许它们 summation 的总和就已经高达原本的 variance 的90%或甚至95%。 实际上到98都可以。那你发现这个 K 值其实可能很小，就10维、15维、20维，就是说新的10维、20维好了，你例子来说，新的 PC1 到 PC20只有20个数字，20维而已，它就已经占了原本资料里面90%或者95%的 variance。所以第21维到第100维就没有用，因为它只占了5%或者10%原本资料的 variance。那我们说 variance 是用来区分资料很重要的一个概念，所以在分析资料的时候，我们就是把大部分的 variance 留下来做后续的分析就好了。所以我们的经验都是在这里砍一刀啊，那一刀怎么砍？我们等一下用 orange 做给你看哈。在这里砍一刀，比如说是20，那我们就把20维留下来，那20维占了原本资料的95%的 variance， 后面5% 的 variance 落在21维、22维一直到新的100维之间。可是你看到这边就有80个数字，对不对？然后才占5% 的原本的 variance。那如果你的资料量超大的话，你愿不愿意放弃这5% 的 variance， 然后去换得你的资料的 feature 本来从100维变成20维？有很多人愿意，因为这样的你分析的资料的 feature 的量少很多嘛。Pca 非常的，我认为它数学有点困难，但它的直观解释还算可以理解。如果你想空间转换这件事情的话 ，If it is still a little bit difficult for you to imagine how Pca works, we will show you later by using orange. Okay, if you have visualized the data, so that it will be more easy to explain how Pca works. Okay, basically when you apply Pca to your data, okay, there are several things you have to notice. For example, how did you define your K value, which means how many dimensions you want to count after you do principal component analysis. Usually, we set a number, okay, by using variance. Okay, for example, I want to hit 90% or 95% or even 98% of the original variance in our new space, which is PC1 to PCK, and that is good enough for me to do the further analysis. Okay, so basically you have to decide what is the K value for your analysis. Okay? Originally, if we have 100 dimensions and now you choose K is 20, then you do dimension reduction by choosing a smaller K, right? 所以你可以借由选择比较小的 K， 然后你就到一个新的空间嘛，K1 到 K20， 而不是原本的 X1 到 X100哈。那么你就做了所谓的 dimension reduction。那你做了维度的缩减，当然有很多好处哈，也有很多的坏处啊。如果你 K 选的不好的话，it is not necessary to have to do dimension reduction. Okay, there are some pros and cons. Pros cons 就是好坏处哈。For example, if you choose a smaller K, it will be more easily for you to compute your model because you have fewer dimensions, right? So let's continue. Okay, you can just read this sentence. Okay, and I would like to skip some slide because we can use orange to do a better job. Okay, so take a look at this one. For example, I believe that is X. Okay, and that is Y. Okay, that is PC1, PC2. The original X and Y, they describe the data, but however, they covariance. Okay, in Mandarin is 就是共变嘛。所谓共变的意思就是说，我们都会算共变数嘛，变因数嘛。所以共变的意思就是说，当 X 变大的时候 ，Y 也会变大，所以 X 跟 Y 是相异的，对吧？你这样看就知道，因为它是 X、Y 明显有个线性的关系嘛。Okay. When we say covariance, that means when you increase X and your Y, because they are covariance, right? And Y increase. When X is smaller and Y is smaller, so the relationship between X and Y, they are related. So we say they have a high variance, or a high covariance. 就是中文共变的意思，就是这个意思翻译得很好但是我们会不希望说你在新的维度里面 X 跟 Y 有，就是所谓的 PC 跟 PCA 有所谓共变的关系。所以 PCE 跟 PCA 一定是我们刚讲过，一定是垂直的，相互垂直的。英文是 orthogonal， 就一定是垂直。垂直的就表示 PC 变大的时候PC 变大的时候 ，PCA 不见得要变大 那他们就互相垂直。互相垂直的话，如果你统计的观点来说，他们就意思就是他们是没关系的了。他们是没关系。Okay. So we don't want to analyze the data with if x and y has high covariance. So we rotate our data using PC1 and PC2 to describe the data, and they're orthogonal. So basically, conceptually, the data plotted project. You can project your data on PC1 or PC2, right? So they are unrelated. They do not have any relationship for data plotted on PC1 and PC2. Okay, and as we mentioned before, how do we find those things? We use eigenvalue and eigenvector to find PC1 and PC2. So the eigenvector is exactly the vector, the direction of the PC1 and PC2. Okay, you may want to revisit Wikipedia, revisit the definition of eigenvalue and eigenvector. And then the eigenvalue is exactly the length, okay, of the PC1 and PC2, which is right here. 就是 eigenvalue 的那个数字的大小啊，那个比例啊，就是我们现在画在这个图上的这个轴，那个向量的那个长度。那 eigenvector 呢，就是这个向量，实际上是垂直，不过没关系，就是那个向量的方向。好，所以我们在解 eigenvalue 跟 eigenvector 的时候，就可以解出来 PC1 跟 PC2 它们的方向与它们的长度，就是它的 eigenvalue 跟 eigenvector。但实际上，我们刚刚中文的解释是说，我们找到一个最宽的 variance 嘛，然后去旋转它嘛，找到次宽的，然后再旋转它，找到第三宽。这两个在数学上是等义的哈，只是在数学上你这样求会比较快，所以你就算 eigenvalue 跟 eigenvector 就可以找到 PC1、PC2 的方向跟长度。好，大概是这样。OK。So we will not go over how to find those eigenvalue and eigenvector. If you are interested in how to find this, you can read this view graph. Okay, so on and so forth. Okay, so I would like to show you how do we perform principal component analysis. Run your orange. Okay, and for example, I have a data point right here. For example, that is I use a very simple data set which is Iris. I have introduced it before. It has 4 features, so we have a 4-dimension. Okay, data right here, and one target which is category data. 3 different classes. So if we plot this data by using scatter, okay, and then we can connect the data to scatter plot, and then we can see that, okay. The x-axis, okay, is right here, right? It says it, and you can change it to either one of the 4 features right here, okay. So you can observe this data, right? However, it is a data set with 4 dimensions, right? And human beings can barely comprehend how data are plotted in the 4 dimension. Let's try to do principal component analysis. Okay, it is under the category of unsupervised learning. It's right here, and here is the Pca. Its input is data, so we directly connect your data, which is 4 dimensions, to principal component analysis widget, and you double click it. Component selection. Since we originally have 4 dimensions, so in this drop box we can select. We like to keep only 1 principal component, or 2, or 3, or 4. And when you click the component, the number of this component, okay, beware of the underline this one. That is expanded variance. If this number 4 is exactly the original. The number of original dimension, this number will be 100%. It means all 100% of the variance will be kept in the new space. 就是说，这个数字，因为你原本有4个 dimension 嘛，对不对？所以这个数字你可以调1到4。那1到4就刚刚讲那个 k 值的哈，你有多少的 dimension principal component 被留下来？那你在看的时候，你要注意看下面这个字哈。所以这个1跟72是什么意思呢？就是说原本的那个资料有4维嘛，4维它们是不是有 variance？ 那 variance 的和应该是一个数字嘛？那假设它是100%好了。 那这个172的意思是说，你转到新的维度之后 ，PCE 这个维度超强的，它一个维度就可以占原本的 variance 那个100%里面的72%，也就是说呢，剩下3个维度才占27%。为什么呢？因为 Iris 这个资料是花朵的资料嘛，对不对啊？一个是花萼，一个是花瓣的宽度跟高度。你可以想，一朵花它长得很大跟长得很小，它花萼跟花瓣的高度跟宽度是不是其实有一种线性的相依性？就是你会觉得它的花萼如果越大，宽度越宽，它的花萼的高度应该也是越高嘛。那它的花萼越大，那它的花瓣应该也要越大嘛。那花瓣越大的宽度越宽，那长度也就越长嘛。所以这4个值应该是非常非常具有共变的，就是所谓的相关系数很大的意思。所以啊，我们在旋转的时候，我们就可以把大部分的 variance 集中到第一个维度。OK， 英文再讲一遍哈。Since the data has 4 dimensions and this data is iris data, is flowers. Supposedly, if you have a large petal length, and we can imagine that its width, petal width, should be larger, so that the covariance between all these 4 features should be large. So that when we do the Pca calculation, okay, the first dimension, PC1, it has 72% of the original variance, and you can increase it to 2. If we kept first 2 dimensions in the new space, which is PC1 and PC2, and PC1 and PC2 can have totally 95% of the variance, and so on and so forth. And you can simply take a look at this brown line. One principal component, okay, the 72%, and the other 2 is 95.8%, and 3, 99%, and 4, so 100%. So basically, we don't have to use the original 4 features to describe the flower data. If you believe, okay, 95% is good enough, and then we simply just choose 2 right here. So that means after we do principal component and we select only 2 principal components, which is 1 and 2, and we can see that. Okay, click this one and it says, for this data point 1, y is setosa iris. The original data is right here, 4 dimensions, but we can convert it to a new space which has only 2 dimensions, and these 2 dimensions have 95% of the original variance. So that is PC1 right here, PC2 right here. However, the value right here, minus 2.2635, that data is a little bit meaningless. It's just a new space to describe the original data. So that we can do one more thing. It's right here. We can do visualization is scatter. Okay, and here we connect it right here, and we can use the new PC1 and the new PC2 to draw the scatter. Here you can see that is PC2, right? That's the new axis. That's new PC1. If we project all the data point to PC1, the PC1 should have the largest variance. All the data will be separated, will be described by PC1. 原本是 PC1 到 PC4 嘛，但我们现在只选2维嘛，对不对？然后我们有2维，我们就人眼睛就很容易看，对不对？所以横轴是 PC1， 纵轴是 PC2。然后你可以把原本的资料呢全部都投影到 PC1 上，那你就会发现 PC1 这个轴啊，好，是数学家告诉我们的，会是最棒的轴，使至于所有的这些点可以散的最开在这个轴上，就是现在这个 PC1 的轴上。然后 PC2， 我刚刚讲它不是垂直 PC1 吗？好，所以就垂直嘛。那你就可以对它做一个投影，就投影到 PC2 上。那投影到 PC2 上之后 ，PC2 上这些值呢，就会是第2高的variance， 也就是把它散最开。所以你看哦 ，PC1 用某一个观点把资料散得很开 ，PC2 用另外一个观点把资料散得很开。那在这个平面上，那些资料点不就散得很开了吗？如果他们原本就有那种 class 的概念的话，他们应该就会散得开开的。那你做 classification 的时候就会比较方便，理论上是这样子。但我们可以知道，因为那个花的那个资料里面， 这两种花其实本来就已经很接近了啊，所以你散的再怎么开，就把红色跟绿色就散的再更开一点点而已。那就要看你后面的 model 有多强，可以把红色跟绿色拆开。但是 Pca 就只能做到这边，就是把资料散开。那你资料散开之后，你就有机会在中间找到一个弯曲的 surface， 然后去把资料切开嘛，所以 Pca 只能做前半部，把资料散开，以方便后面的人，后面的 model 来做事情。Okay, the next thing we have to say is we add another data table right here, okay, behind the principal component analysis, but we do not pass the data, the original data or data to the data table, okay. Instead, we connect this one, component, okay. So what does that mean? That is, as we mentioned before, Pca is some kind of rotation in space, right? And it has A1, A2, A3, A4 to D1, they have a lot of factors to describe how to rotate the data. And here is the parameters. So PC1 equals 0.62 times Septovan plus minus 0.263 times septal width, and so on and so forth. So that is the factors, those factors. Okay, you can output those factors. I would like to show you something. Okay, original data will be right here, right? Let's use two different data. Okay, the first one is original data. So let's remove this one. Use the original data right here. Okay? The upper data table, which contains the original data in the original space. Okay, so we have 4 dimensions. Okay, and we select the transform data right here. So at the bottom data table right here, okay, it only contains the transform data, okay, which has only 2 dimensions right here, right? We'd like to do an experiment, okay, and we use this logic regression and SVM and maybe tree. Okay, these 3 different algorithms, they all belongs to supervised learning. They can do classification, right? We connect all those algorithms to the test. Okay, that is the upper one, and we do the same thing. However, we connect it to different data source. Okay, one of them, the upper one, use the original data, which has 4 dimensions, right? So we use the original data, which has 4 dimensions, to do such kind of experiment. Okay, the other one, the bottom one, we use the Pca data, which has only 2 dimensions, right? 2 dimensions. So let's take a look at the upper one. If we use the original data, which has 4 dimensions, you can see that, okay, linear logistic regression, remember this number, okay, 98.7%. But if we use transform data, well, we have only 2 dimensions, okay? The result will be the classification accuracy decrease. Why? What is the reason why we don't have better result if we use only 2-dimensional data? Because, as we mentioned before, 5% of the variance has been discarded. We remove 5% of variance. So we have only 95% of the information of the original data to help us to do such kind of classification. So theoretically, if you remove information from your data, your classifiers like tree, SVM, or logistic regression, the classification accuracy decrease. 好，中文再讲一遍啊，因为我们已经拿掉了5% 的 variance， 那5% 的 variance maybe 他们就是这么的厉害，那5% 的东西可以把原本的某些点稍微的再分开一点点。 可是因为我们现在选择2，选择2的话，就是把那5%的东西丢掉嘛。那你 information 丢掉之后，或许本来某2个点，因为那5% 的 variance 是可以分开的。可是因为现在你那5% 不要，那2个点就更靠近了，或者是根本就重合在一起了。那根本重合在一起之后呢，你后面的 classifier 要处理这些资料就更困难了，所以它的 accuracy 不见得会上升，好吗 ？Okay, let's take another experiment. Okay, remember this number, loss regression, 91.3%. Okay, if we have only 2 principal components. Okay, we can simply change it to 3, so that we have 99.5% of data, and we can describe it by using 3 dimensions. Okay, and then let's take a look at the result. You see, it increased, which means I have additional 4.5% variance. Okay, I use 1 dimension. I use 1 additional feature, which is PC3, to describe 4.5% of the original variance. And then you can see that the accuracy increase, and so on and so forth. If you include more dimension when you do principal component, and it might increase. Okay, so it depends on you how to choose K. You have to take a look at the classification accuracy and the number of variance, sum of variance left in your principal component to decide what is the K, what is the principal component you would like to use. 好，所以你要综合稍微考量一下哈，你可以做一些简单的实验，做一些简单 classify 的实验，看看那个 classification rate 是不是你喜欢的，然后你可以稍微调整一下你的 K 值，大一点、小一点，保留足够多的 variance 去描述你原本的 data。啊，你既可以减少 dimension 的数量，然后又可以维持在一个高的 variance 跟一个高的 classification rate， 那个你自己决定。好，这都要看资料做自己决定。